All right. Good morning, good afternoon, good evening, whatever time you're watching this lovely video. Today we're going to work on 6.3, proving quadrilaterals are parallelograms. Yesterday we talked about parallelograms in general. This lesson is going to be a lot like yesterday's lesson, and it's kind of one of those converse lessons. We've had a couple of them in the past where, we're proving one thing, then the other, and then we switch it, and it's pretty much the opposite. So this is another one of those. Today's lesson objectives are to prove that a quadrilateral is a parallelogram and to use coordinate geometry with parallelograms. You're going to love the coordinate geometry of parallelograms, all the fun things that you can do with that. It's going to be so much fun. Alright, I'm assuming that you've had the opportunity to write that title. So let's review. Name 4 special things that you've learned about parallelograms yesterday. So parallelograms have blank. Well, what's special? What is the definition of a parallelogram? What makes a parallelogram a parallelogram? And it's the fact that you have 2 sets of parallel sides. Knowing that this means parallel. You got that? I'm going to be real upset if I get a hand raised or somebody coming in and what was that? There's 2 little lines that you drew sideways. They look kind of goofy. Those are parallel lines. Notice that they're not intersecting, showing that they're parallel. They're going in the same direction. Okay. So parallelograms have 2 sets of parallel sides. What were the special things that we talked about in that last lesson? What were the special things about the parallelogram? If you had a parallelogram, what did you know about opposite sides? Opposite sides were congruent. What did you know about opposite angles? What were opposite angles? They were congruent. Then what do we know about consecutive angles? What do we know about the angles that were adjacent to each other? So the top and the bottom, or the left to the right. They're supplementary. They add up to 180, right? And then our last one, we have one more. I talked about the diagonals. The diagonals what? The diagonals bisect each other. They cut each other in half. They're literally bisectors of each other. Both cut each other in half. Alright? So, there's 5 big things out of that lesson. You have 2 sets of parallel sides. The opposite sides are parallel, both sets. Opposite sides are also congruent. Opposite angles are congruent. The adjacent angles, or the consecutive angles, are supplementary, and the diagonals bisect each other, cut each other in half, cut each other into 2 congruent parts to each other separately, right? So, like I said before, today's the converse lesson. It's where we're switching our parts, right? So, a lot of the same type of definition that we used to say, but it's just changed just a little bit. So now what we're saying is we're looking at a shape. If we're looking at this shape right here, we see A, B, C, D. And we can see that both sets of opposite sides are congruent. Both sets of opposite sides are congruent here. You know that's true for the parallelogram, right? We talked about that yesterday. If you have a parallelogram, then opposite sides are congruent. This is saying the opposite. Say if you're looking at this shape without all this theorem right here that you're getting upset that I'm blocking, you look at this picture right here and you saw these opposite sides congruent. You should be able to think in your head and say, well, I know parallelograms, they have opposite sides congruent. And that's what we're doing here. That's what we're talking about in this theorem. That's what we're talking about in this concept. You can look at a picture and you're identifying. You have to be able to identify. So you see those opposite sides, you say, I at least know that this is a parallelogram. Same thing here. Without looking at this theorem right away, look at this picture. You're seeing you have 2 sets of opposite angles congruent. Angle A is congruent to angle C. Angle D is congruent to angle B. 2 sets of opposite angles congruent. You remember from yesterday's lesson we talked about opposite angles are congruent in a parallelogram. So, if you see that you have opposite angles congruent here, that means this must be a parallelogram. The quadrilateral is a parallelogram. Our 4-sided figure has to be a parallelogram if opposite angles are congruent. I'll give you a minute. Write this down. It's not literally going to be a minute, but I'll give you a little bit of time. This could be a great time for you to pause if you're on your own video. But, yeah, Fun stuff. Alright, let's move on. And again, you can pause this. Pull it up on your phone, pause it at the 5-minute 20 mark. Alright. So we're going to keep on moving in that same direction, the same thing we were talking about. What are the two special things that we talked about? We talked about consecutive angles, right? So, we're looking at this parallelogram. Well, I'm sorry. We're technically, we see we have a quadrilateral because we have 4 sides. We know this is a quadrilateral. We're wondering what type of quadrilateral it is. The only thing we've talked about personally right now is parallelogram, so of course, it's the only thing you could be thinking about. But you're looking at this, you're seeing that these two angles are going to end up being supplementary. You're seeing you have one set of opposite angles congruent. You don't know about this angle. You can't say, oh, well, the opposite angles are congruent, because we don't know this guy C here. But these two end up being supplementary. Angle A plus angle D. And technically, I should be throwing in a little measure things, because the measure of the angle, the measure of angle A and the measure of angle D will add up to equal 180. And the same with angle A and angle B. So if the measure of angle A plus the measure of angle B is equal to 180, then we would know. If we knew that both angle D and angle B both add up with a equal 180 individually, A plus D equals 180, A plus B equals 180, both of those added up to equal 180, then we would know we would have a parallelogram. Yesterday's notes, we said, hey, if it's a parallelogram, then we know consecutive angles are supplementary. Now we're saying, hey, we're going to figure out if this is a parallelogram. We're going to add up these angles and see if they add up to 180. We're going to add these two angles and see if they add up to 180. Oh, and they do. Yay, it's a parallelogram. At least for this general example. And we have one more here. That's Theorem 611. Alright, so Theorem 611 talks about the diagonals. What do we talk about with the diagonals? They have to bisect each other. They have to cut each other in half. So if you're looking at a quadrilateral, or four-sided figure, looking at a four-sided figure, and we have diagonals that are drawn, and they actually do cut each other in half, then we have a parallelogram. Back from our lesson yesterday. Parallelogram, diagonals bisect each other. So today we're saying, hey, the diagonals bisect each other, then it's a parallelogram. It's going true in both directions. I'll give you a minute to write this. If you're wondering why I'm being so repetitive, it's because I'm trying to beat this into your head. The whole general concept here. We're just switching everything that we did from yesterday. Now I'm going to throw that nice curveball at you. I told you about that coordinate geometry. That's going to be a fun one. But we're not done. There's one more special case that makes this today's notes a little different than yesterday's. Okay? We have one more special property, one more special occasion, situation about proving a parallelogram is a parallelogram. Ninja style. Okay, if you need to pause it, right now would be a good time to pause it. Alright. Theorem 612. This one is our special case. It doesn't go in the opposite direction because you already know that opposite sides are parallel, you know opposite sides are congruent. So if you want to figure out, though, if you have a parallelogram, if you can show that one set of sides, the same set, has to be the same, same set of sides. If you can show the same set of sides are both parallel and congruent, then you know you have a parallelogram. The same set. So I couldn't I wouldn't be able to show AB parallel to CD and then go and try to figure out if AD is congruent to BC. We wouldn't be able to prove it's a parallelogram. It might be. You could have a parallelogram there. But you can't prove it in that case. But if you can show that AB is parallel to CD and also congruent to each other, AB is congruent to CD, then you know you have a parallelogram. You can prove it. It's guaranteed. That's what this is saying to you. You're allowed to say that. Not going into all the fun of why, cut proofs out. You just love those. I know it. That's why, I had to pull them out. I felt you might love geometry a little too much if I added in all the proofs and all the fun in that. So, let's just worry about our general concept here. If you can show the same set of sides, that one set is both parallel and congruent, you got yourself a parallelogram. Giving you a few seconds, write everything down. You're loving it. You're loving it. There's a great opportunity to pause it, which is meaning that I'm going to move on now. All right. So, we're going to show that these four coordinates, A, B, C, and D, are the vertices of a parallelogram. You're saying, oh my God, I got four coordinates. You're going to show that A, which is 2, -1, B, which is 1, 3, C, which is 6, 5, and D, which is 7, 1. You're going to show that these vertices are the vertices of a parallelogram. I'm going to add something. This is going to be special. That's how special this is right now. We're going to search X, Y, graph. Oh, we're even going to graph this. I'm going to cut down on my room a little bit, but that's all right. That's all right. So A is at 2, -1. Loving the smart boards off. I just need to recalibrate every morning. Alright, B is at 1, 3. C is at 6, 5. And D is at 7, 1. D, C, C, D. So we're looking at this picture. I'm not the greatest artist I know. It's kind of looking like a rectangle in a degree, but in general, when we're looking at it, it looks like it could be a parallelogram. We're showing that it is, so technically we are going to prove that it is. It is going to work out here. But how are we going to do that? What do we do for coordinates? We have a couple different things, right? With coordinates, we do distance formula. That tells us length, right? We use slope formula. Slope formula tells us what? Parallel. Tells us something's parallel, perpendicular. It's just general slope. Tells us the slope of line, right? Is there any other ones? Use midpoint. Good back there, Jack. Great job. x1 plus x2 divided by 2. y1 plus y2 divided by 2. So if we're thinking about it, everything we talked about today, everything in our lesson today and everything in our lesson yesterday, a parallelogram has two sets of parallel sides, two sets of opposite sides parallel. Which formula will we use to show that? Slope. Parallel. Use that to show them parallel. So we could find the slope of all four sides, and we could figure out, it's 4 steps, that's 4 times we would have to do the work, but we could figure out if this is a parallelogram by finding all 4 sides parallel. It's one option. It's a smaller formula, so it's not too bad, right? Then our first theorem was opposite sides are congruent. If we're going to show opposite sides are equal in length, then that must mean length. We're going to have to use distance formula. Distance formula 4 times. Killer. Killer. But still, practical, fun. Love it. Just a little more work compared to slope. But, alright, so we have that. We have opposite angles congruent. We would have to measure the angles of this if we had a compass. I guess we could measure it. Could be some human error there, and especially with my smartboard being off, if I went to measure these angles, they're not going to be perfect. It's going to be a little off. Consecutive angles, supplementary, same thing. Draw line, that could be off. So, the angle situation is not going to work. Diagonals bisecting each other. Ooh, diagonals bisect each other. That means they cut each other in half. That means finding the midpoint. Alright, well, we could find the midpoint, and then from there, we would have to use distance formula 4 times to find each piece. We think about if we had the midpoint here, we'd have to find the distance from B to the midpoint, D to the midpoint, A to the midpoint, C to the midpoint. That'd be 4 distance formulas on top of doing the midpoint formula. That sounds like a lot of work. Probably the most work out of the group. Oh! And then we had our new theorem that we just talked about. That we show one set of opposite sides both parallel and congruent. That means showing BC's congruent and parallel to AD. That means we have to do the distance formula for both sets of opposite sides, and then do the slope formula for both sets of opposite sides. So I'm going to give you a second. You can think about it. Alright. Just for the fun of it. Hey, Lee!
Hey.
Alright. Somebody actually said hello. It's Ghost. The person's not really here. Alright, so we're actually going to do... Can we get the phone out of here? Ghost? Jesus. Alright, so... we're going to go to that last theorem. We're going to show that one set of opposite sides are both congruent and parallel. You do... Okay. Alright, so I'm going to erase this midpoint formula. Take that away. Let's go with BC and AD. Let's show that they're both congruent and parallel. So, first off, we've got to set up a distance formula for BC. B we know is 1, 3, and C is 6, 5. So we subtract our x's, so we're going to do 6 minus 1. We're going to subtract our y's, 5 minus 3. 6 minus 1 is 5 squared. 5 minus 3 is 2 squared. Square root of 25 plus 4, which is the square root of 29. I'm get all mad because I'm covering up, so I'm just going to give you an opportunity to write that. let's find our distance of AD. A being 2, -1. And D being 7, 1. Let's see if our distance ends up being the same. So we set up our x's are 7 and 2. 7 minus 2 squared. Our y's are 1 and -1. I almost thought that was a 7. Woo. 1 minus -1. Seven minus 2 is 5 squared. 1 minus -1 is 1 plus 1, right? So it ends up being 1 plus 1, so that's 2 squared. Look, we're already set up the same. We're going to get that same answer. 5 squared is 25. Oh, and the board wants to restart itself right now. That's always nice. All right. So it's 25 plus 4, square root of 29. They're congruent. Positive. It's a good thing there. AD congruent to BC. That's half our work. I know what you're saying. You're like, Jesus, we were flying through these notes. Now we're doing this coordinate stuff, and it's like, this is like half the video. Oh my God. You'll be alright. You'll be alright. Alright, so now we've got to find the slope of BC. Which we know is y2 minus y1 over x2 minus x1. Okay? So really we're doing the same exact thing here. For our y's, we're 5 minus 3. Our x's were 6 minus 1. The great thing is we've already done the math for that, right? So we have 5 minus 2, or 5 minus 3 is 2. 6 minus 1 is 5. So we have a slope of 2/5. We're almost, in that same degree, we're almost noticing this is going to work out again. If you're thinking about it logically, since we've already done that subtraction, we've already gotten the same numbers for our congruence. If you don't notice it, no big deal. Now we'll do the slope of the other one. So slope of AD, or y2 minus y1, is 1 minus -1. And we have 7 minus 2. Hi, Jen. Hi. 1 minus -1 comes plus. So that's a 2. 7 minus 2 is 5. 2/5. 2/5. That means we know that AD is parallel to BC. I'll give you a second to write all this, look at it, soak in. Again, another Mona Lisa, 16th Chapel, Statue of David. Some of you might be the thinker right now. You're asking, though, I have to do all this work every time? Well, pretty much. I mean, you can show both sets of opposite sides are parallel. Just do the smaller slope formula 4 times. That would work as well. But you have a lot of different options. So take which ones you will. Now, if in the directions they ask you to do it one specific way, you have to do it one specific way. But if the proving it's a parallelogram with the coordinates is an open question, I say, hey, show the 4 parallels. Show all 4 sides that are, 2 sets of opposite sides are parallel. Show that. It's better. It's faster. Okay. You should pause it now if you need to write anything else. All right. So this is our closure here. We got to state the 6 ways that you can prove a quadrilateral as a parallelogram in general, not just with the coordinates, in general. So this will probably be me pausing right now for you to write those down, because this is a closure question, meaning I want you to answer these. And I'm going to do my best Wheel of Fortune lady move. I mean, and I'm far prettier, but it's okay. I can handle it. Not dressed as fancy today, but it's okay. Alright, so first one, opposite sides are parallel, the definition of a parallelogram. We know opposite sides are parallel. Said a bunch of times, opposite sides also have to be congruent. Opposite angles have to be congruent. Consecutive angles have to be, don't say congruent, supplementary. Diagonals have to bisect each other. And then our special one from today, one pair of opposite sides are both parallel and congruent. So that's the lesson for today. You guys have your syllabus, you know what your 6.3 homework is. We might be working on that on Monday if maybe I give this to you for homework. We'll see how class goes. All last day, 2015. Chatters in the back. Have a great day, guys.